So, welcome everyone. First of all, I want to thank everyone for joining this session. This is going to be a town hall session, so with the objective of starting collecting feedback from the community on a couple of initiatives that we are addressing to have a story around eBPF on Fluent Bit. So yeah, as I said, welcome and thank you for joining. We are going to be spending some time going through the following topics. So we are going to start with an introduction. We are going to be talking a bit about what is eBPF, as I recognize that even myself, when starting reading about eBPF, I wasn't clear on the entire capabilities that eBPF can bring in the Linux introspection and tracing space. So I will be covering part of that, clarify a few concepts that are important, and then we will be spending time understanding how we could benefit in the Fluent Bit project from using this technology. Then I will be spending time as well talking about the state of the art of Fluent Bit plus eBPF. What are the existing level of integrations? What might be the limitations on those as well? And then going about like two proposals essentially and collecting feedback from the community on those two proposals. So yeah, let's get started. So who I am? Well, my name is Jorge Niedbalski. I'm an open source contributor and maintainer on Fluent Bit since around 2021. I work as a member of technical staff in Chronosphere. Previously, a Calyptia member, worked for Canonical as well, and Linaro, always related to Linux, observability, systems performance, and these aspects. So my personal website, it's linked there. You can jump there and see if there's anything interesting. What is the motivation from my side for this presentation? So the motivation is to present an initial proposal about how we can leverage Fluent Bit to use eBPF, and also listen to the community on the use cases that we should support. So obviously, we want to start with baby steps on this integration, see if there is value that we can see there from the community, and then see how we can leverage and extend in this position for Fluent Bit. So yeah, that's the motivation. Okay, I'm going to start covering what is eBPF from a technical perspective. First of all, eBPF, it's a virtual machine, right? It's a virtual machine that can be instantiated by the Linux kernel. So this puts this technology in a very interesting space because it's a virtual machine that can execute code under the Linux kernel domains. So that means programs can be loaded from user space, opening a possibility of doing a lot of things that are interesting from the introspection perspective. The programs that are written for eBPF are loaded as bytecode. That bytecode is precisely compiled into from a subset of C, and then it's verified as well. And you might ask yourself, why is it verified? Why is it constrained? I will go into the details of that, but essentially think about it as very constrained programs that can execute code based on events that are generated in the Linux kernel, right? Also, it has to be very performant because in ring 0 or in kernel land, it's very important that you don't hijack the execution of any function. That time is limited, so it has to be pretty effective in terms of system time that is spent in that code. So that's why, as part of that VM job, is also make sure that the time that a program is running, kernel time, is limited as well. Also, it converts part of that bytecode into native matching code for better performance as well. So the VM, although seems to be pretty simple, it has some complexities. So I probably won't enter into that much details about what the VM is about, but it's essentially, it has a stack that is also limited for local variables as part of each program. That stack is constrained, I think, to 512 bytes. It has 11 registries, one of them used for return values, another one, the classical stack-based memory access. The verifier, as I said, given this is code that will run in the kernel space, it's important that that code is limited in scope. So it will have a sandbox. That code cannot run arbitrary system calls. It cannot run arbitrary I/O operations. It can use a very limited and curated set of helpers from that program. So that's its sandbox for that program to be limited. And as I said, the verifier, which is the component that makes sure that that code is doesn't perform any invalid memory access. The program runs with an instruction set limit and within the stat limits as well. So this is to say, the bytecode compile program is very limited in scope, in the amount of instructions, in the amount of operations it can perform, and also in the kernel functionality or surface that it's able to access to. As a matter of graphical approximation to this, so you will generate bytecode from a compiler. Typically, you will use Clang that will generate eBPF bytecode, and then it's loaded into kernel land by the program. First step is to run the verifier, ensure that, as I said, the amount of instructions is limited, no random access memory, the amount of helpers that that program is accessing to is limited. And once that's done, that eBPF program can react to different sort of events as part of the kernel. So I will get into the details about what those programs might be. It can be kprobes, it can be uprobes, it can be trace points that are already defined in the kernel. Performance events, I don't think I will cover performance events, but that's something that also it's able to hook in that eBPF program. And then obviously you might need to read data out of those programs from userland. And typically what you will do is that you can interact with that program through system calls, or you can use, in the case of eBPF programs, you can use a data structure called maps, right? So I will cover a bit what those different maps are, etc., and how you can use it. But to have an idea, userland can only talk to the eBPF program through those maps. So I just explained the eBPF program lifecycle is pretty much these 6 steps. So first of all is compile the code into eBPF code. Then you can load from userland that bytecode using a system call. Depending on the program type, it will have access to different helpers and functionality. Then that has to be attached. So you need to say, okay, this program is attached to these specific sets of events in the kernel. Whenever the kernel reaches that event, it will execute then that attached program. When that happens, if that program needs to check data, write data, or initialize data, it will use maps. Essentially, that's the way that the program will interact with. And then once that execution is complete, the program is unloaded. So yeah, that would be like the basic life cycle. In terms of the program types that you can have, right? So those will define effectively what kind of attachment types it can do, right? So, and these will have pros and cons, correct? So you have, so I pointed here 3 types. You can go in detailing like the many, I think it's like 20 something or more than that program types, but the most used ones are kprobes. Kprobes allows you to essentially set up and interrupt handler in any part of the kernel, right? So you can attach to very specific functions in the kernel. But not only that, this same approach has been extended for also allowing userland. So let's say that you have a binary, it can be Fluent Bit, and you would like to attach into a particular function. You can do that using this same program type app and technology. Also, what is important is that you can attach to a program in two places. So you can attach to a function when it's entering, and in that way, when the function gets called, you will get a reference to the context of that function call, namely all the registers that you have in that function call. And also you can do it in return. So whenever that function is returned, you can do like a trampoline call, get the return values, do something with that, and inspect. So, and this happens also for the userland code. So if, let's say that you would like to hook in at the exit of that function, you can do that as well in the using this URED probe. So this is very flexible because you can attach to a specific function, but obviously it has a performance impact, right? Because for implementing this, you need to set up an interrupt, do a context switch, jump the execution into this context switch handler, and run the code and then return back. So it has a performance implication. But at the same time, it's pretty flexible. Then you have trace points. Trace points are effectively for system call, scheduler calls. So trace points are defined in the kernel. So you have trace points that you can jump into. Those are predefined. It doesn't require an interrupt. It's less flexible for arbitrary functions, but also it allows you to use the existing tracing infrastructure. Also tracing, which uses the infrastructure set up by ftrace, essentially fentry, fexit. It has a low overhead, but it requires to use ftrace supported function, essentially. And the performance impact is minimal in this case. So also, again, program types is very expanded. You can go through the list and take a look at the ones you have there. But I think I have covered the most important ones here. So yeah. And then now that we understood kind of, okay, what is a VM, what it will hook into the different events, what are the kind of programs that I can run, and what are the limitations of those programs, I would like to briefly cover one or two very simple programs to understand the point that I just explained. So this is a typical, very basic eBPF program. So here the program, you will see that there is a set declaration. That's a macro for declaring the program. So in this case, I'm saying, okay, this is a trace point that will be attached in the openup system call, and this will get executed at entry point, right? So whenever this function gets called in the kernel, I will get an event, and my code, this function that I have under, will get executed, right? Of course, I will have a subset of helpers available for accessing different functionality here. Part of that is going to be, you can use BPF tool for seeing what are the what are the features and helpers that are available for this particular type of program. In particular, in this program, I'm doing two important things. First of all, is that I'm declaring a ring buffer. I will get into the details of what a ring buffer gets used by, but in this case, it's a fixed data structure of a fixed size that I'm using for passing data to userland from my eBPF program. So in this case, I'm reserving some data that is the size of the event. Event is a type that I have defined somewhere. And then fill it data structure with some specific data. In this case, I'm doing two things. First of all, setting the process ID. And by that, I'm using another helper, which is called get current bit. And then I'm using the read user string. So even though not all of the eBPF programs can access memory from, user memory, there is a safe way that eBPF has through this helper to read memory from, to read from user memory. In this case, I'm just populating with the file name that it's getting open and then submitting that data into a ring buffer. So this might be probably the most simple example of an eBPF program. Okay, then another example of another eBPF program. In this case, I'm declaring a program that will use kprobe. As I mentioned, kprobe is a technique that will hook in like any part of a user land or kernel function. It will get hooked in this case. What is interesting is that in this case, I'm tracing Fluent Bit itself. So I'm dynamically inserting a breakpoint on the FLB input log append, which is the function that will append a log entry for the internal Fluent Bit pipeline. And what might be interesting here is that, so particularly, I would like to know from user land, what is the amount of data that I'm sending to the input log, right? So I would like to keep track of that. So I wrote this program. I set up an uprobe that will set up a kprobe for this in the FLB input log append. So whenever this function gets called in Fluent Bit, I will get in this case, the buff size comes as a fifth parameter. This one requires ptrace capabilities for that uprobe. I read that data and I send it in the same way into a ring buffer. So this is kind of a more advanced example using userland, but it's just to exemplify that another type of program can also do interesting things. So there's a program there that you can follow in my blog with some other examples and how to read that data out of userland, particularly from Goland. So yeah. So as I mentioned, the eBPF programs can only use this set of defined structures called maps. And the amount of maps is like massive, and I won't cover all of them, but I will cover the 4 like modules. So you have a hash type, which is essentially a key value. You can use it across all program types. It has some limitations, so it has a fixed size. Also, deleting a key out of a hash map has to be explicit. It's not that they get removed automatically. For an array, it's essentially an index key with integers. You can use it in any program type. Also, the limitation is that it has a fixed size. And once it's defined, you cannot modify. So it's a static sort of thing. And then a ring buffer, which is essentially for streaming. I send data, I reserve data, and set data, I copy data, I read data, and so on. So also it has a fixed size in terms of elements or data that you can write to the ring buffer, but essentially it's a circular sort of. And the limitation I would say is that it requires polling. So from userland, you can set up a poll and await for data to be written into the ring buffer. But this is a setup that you need to do. So that might be a limitation here. Also, there is like new program types that you can have like a program array. So in a way that you can do tail calls. I'm not going to explore that as part of this presentation, but this is something that it's getting traction. Okay, and a last example here to cover the maps. So essentially, as I explained, my eBPF program can communicate through a ring buffer. The API for talking with and generating a ring buffer is explained here. So in this case, I'm defining a ring buffer called events that it has this size AK, and from there I can do things like reserve data, submit data. At the other hand, the userland program typically using libBPF or but you can do it natively with BPF called Bit. What leverage most of the user-learned programs that talk with it's eBPF at the moment. So you have a singular API, so you can consume from a ring buffer, you can pull from a ring buffer, and then you will have the map file descriptors for those ring buffers in your program. So I would say that's the basic workflow from reading and writing data. So hopefully that gave an overview of eBPF. So no limitations. So I know that there might be people here that know much more than myself in terms of what are the limitations. So these are the limitations that I found while experimenting around with eBPF and working with it. So one of the main limitations is with older kernels. Older kernels doesn't have what is called BDF. BDF is essentially metadata that describe what is the data structure, what is on it, what are the fields, what are the offsets, what are the size, so that when you are loading a program that uses some data structure, you can understand through what are the relocation entries, and that can be resolved in load time, correct? So for this, there is an implementation that is called core, or compile once, run everywhere. So this allows for the same eBPF program to be compiled a single time and be run across different kernel versions without having to do all the symbol lookup, offset resolution and size. But for this, the programs are using, they can provide some BTF data that has all the relocation data entries on them. As far as I understand, this works in kernel 5.2 onwards. In older kernels, the BTF metadata is like not entirely accurate. Also, another problem that there is with eBPF program is that the instruction count is limited. I think it's limited to 1 million instructions, although this has been increased recently. But the basic idea is that if you have a limited amount of instructions, your program also can be limited in terms of what is the time that it will be spent running. So that's why it has this limitation. You can increase it via syscontrol, by default, it will have 1 million instructions. So if your program eBPF ends up being too complex, and the reasons for an eBPF program to be complex are different, right? So for example, let's say that you are working with file systems and you are hooking into a particular function that access inodes, and you would like to resolve the path to which file that inode belongs to, you will have to unroll all the path down to, up to the BFFs layer, etc., understand what that file is, and that will make things very complex. Same if you are doing sockets, same if you are going to try to translate an IP address or any operation that requires, will make your program more complicated. That's why we have tail calls right now, which allows you to like segment and pass data between different programs. But if you have a single program, that complexity will grow, and that won't fit probably into 1 million instructions. So you will have to simplify the program. There is no dynamic memory allocation. So that means you cannot do a malloc, you cannot do an mmap from an eBPF program. You have to use maps. Obviously, attaching into kernel requires ring 0, right? So you need to be root in order to do that. And also the kernel functions that you can access are limited to the helpers, correct? And also you don't have access to user memory. Those are the limitations that I face on. There might be much more, but those are the ones that I can name. So yeah. Okay. So how Fluent Bit can benefit from eBPF? So you might asking yourself, okay, but how Fluent Bit can use an eBPF program to get anything useful, right? I would say it can actually benefit from eBPF in different ways, right? So you have trace points that are across the entire kernel. You can install tracing hooks in the kernel, and in that way, we could potentially increment the numbers of event generators. Right now, we generated only a subset of events that are very oriented to particular pieces. So for Docker, we have Docker events. For Kubernetes, we have Kubernetes events. obviously you have other inputs that you can integrate with. Let's say you can integrate through forward to any of the inputs, send events, etc. But native event processing just happens in those places. So if we would have access to all the kernel functionality from Fluent Bit, you would be able to expand the amount of event that you can generate, correct? So from a tracing perspective, that's interesting. We can trace events from all system calls. We can trace events from userland programs through uprots or ftrace tracing points across the stack. Gain visibility to Xdata part, sockets information, performance counters, etc. And this will allow to be independent of external tracing tools. So, okay, existing eBPF support in Fluent Bit. First of all, Fluent Bit doesn't have a native way for eBPF programs to interact with, right? So let's say you have an eBPF program that is running, collecting some specific data. Unless you have an intermediate piece of software that does the translation and send it into some output format to Fluent Bit, there is no way to do it natively, right? There's no ability to load and attach programs natively from Fluent Bit. There's no ability to hook in from a map directly in Fluent Bit. And Fluent Bit doesn't expose as well any write channel that is performant, right? So there is no shared memory communication that an external program can use to push information into. There is no shared Unix socket that a program can use to send data, etc. So eBPF program that generate traces, of course, as I just mentioned, can use regular input, but both of them are like limited in terms of performance. So one of them is forward protocol. Forward protocol is a protocol using Fluent Bit that is pretty efficient, but is limited to the network latency regardless. So if you are in a saturated network, that will have an impact. If you have a large latency in that network, that will have an impact on the amount of events that you can generate. And file system, so essentially whatever the file system latency is limited to. So you are writing into file system, you are reading out of it, the bandwidth that you are limited is the file system. So I would say that's generally the existing support. So existing support in eBPF, right now we have two agents that support Falco and Tracy, both using forward. The issues with these agents is that those are external process. You need to set the RAM if you are running Kubernetes. That will means that you will need to have a daemon set that is running with privileges at the host, forwarding that data into your Fluent Bit forwarders. So all that is infrastructure setup. It's also costly because you have two processes for essentially accessing tracing information. So it adds more complexity into the setup. And as I said, this is dependent on integration latency. So existing support, one of them is Aqua Security Tracy. It's something that Patrick Stephens implemented. It's supported in Tracy. I would like to do a quick demo. Let me see, I have some minutes, so probably I would like to cover. So setting this up is actually pretty simple. So essentially, if you run Tracy with all sort of events enabled on it, it will have, I think it's 100 and something different sort of traces that are enabled by default. In this case, I'm using the forwarding protocol to send events to Fluent Bit. And Fluent Bit is going to run just native Fluent forward. So we are going to like a quick run here. Run Tracy at the other side. So what should happen is that this will instantiate different eBPF programs and will start generating data to a ring buffer. Once that data is populated with other information such as the host ID, etc., we are going to start getting events. So this integration works, I would say, mostly out of the box with forward output. So yeah, there you can see different events being gathered out of eBPF. from Tracy. Okay, that's a quick demo there. So you can effectively get events out of Tracy thanks to this work done by Patrick. So thank you, Patrick, for doing that. Okay, so now let's talk about Fluent Bit plus eBPF. Why we can think that Fluent Bit is a good choice for eBPF? That I can think of 4 reasons, right? So first of all, Fluent Bit has already a low resource footprint. So Fluent Bit collector doing like generate collectors through timers and pollers, etc. in terms of resource usage and memory is really limited. So low resource footprint is the first option. It's already designed to run collectors efficiently. So the Fluent Bit uses the concept of collectors already. All that is handled very efficiently. Then it makes sense for it to be an integration point for an external data. Let's name it ring buffer. Let's name it any piece of data structure that we can hook in and get polled. That's a good candidate for Fluent Bit to integrate with. Also, another important bit is that Fluent Bit already runs as a daemon set with host access in most deployments, so you can find it already with elevated privileges. So let's say that instantiating eBPF in those setups is a possibility, so it makes sense for Fluent Bit to run over there. And also there is another thing that is important, which can be bundled as a single binary, right? And have the eBPF program bundled into Fluent Bit. So it's a good place to put eBPF programs into, and why not? Let's explore and see if that makes sense. So there are 2 proposals. One is Fluent Bit as a generic eBPF program loader that I will cover. And another one is how we can expand Fluent Bit to be a trace collector. So yeah, let me go through those. So Fluent Bit as a generic eBPF program loader, right? So let's say that you have an eBPF program, you would like to load that program and essentially hook in the events that those programs are generated into Fluent Bit. That's the basic premise. So user-defined programs can be loaded directly by Fluent Bit. Events that are generated through ring buffers are consumed, and those are flashed into the processing pipeline. Multiple eBPF programs can be loaded simultaneously. And also another possibility is that arbitrary generated data on those eBPF maps can be consumed from Fluent Bit. And the limitations are that programs will have to use ring buffers, program needs to be accessible. So if your program is compiled locally, then Fluent Bit will need to have file system access to those programs. So that's a limitation. Also, there is no general approach to serialize structured data. So we are sending data to ring buffers. That data comes in a particular structure. There's no way that we can know beforehand what type of data is that. Although we might have some type-defined event structure for being able to marshal effectively, that's not supported in the existing program loader. So also that it requires Fluent Bit running as root for loading those programs. So the configuration that we have there is similar to what I'm showing here. So you essentially are indicating what are my BPF object files, what are those, what is the program name that I'm going to load, and what is the ring buffer that I will consume events from. So as an example, I put here a very, very simple example, right? So this would be a trace point that will be captured whenever a system call enters for exec. So whenever I'm executing a program in a Linux kernel. From here, I'm just getting the command out of the arguments and essentially sending this data as an event in the ring buffer, right? So that's a super simple example. So yeah, let's do a quick demo. I think we can show here how those work. they have it compiled over here. So so I have a very simple test configuration. My program is loaded here. Right, so my eBPF program is essentially the same program I showed. I will get unstructured data, which is effectively a string, submit it into the buffer, and read it from Fluent Bit, essentially. So let me go over here. Okay, as you can see here is loaded this eBPF program. It's awaiting on that ring buffer. So I'm effectively loading an unknown event type because it's not defined anywhere. And as you can see, I'm capturing except the executables out of that. Yeah, so my system is generating a lot of Docker things and data here. But okay, so I think that's like the basic example of usage here. You can obviously load multiple programs. So there is another program there that will handle file system events. So yeah, essentially you will start seeing a lot of data that comes in my system, all the events that are generated whenever a file is accessed, open up in my system. So yeah. Okay. So that's the first proposal, is essentially being able to load a program, react to events, and then them. The second approach is how to make Fluent Bit generic trace collector, right? Which means the community and we can leverage the development of traces that are on tree. So we can essentially set up traces for different parts of the kernel and start growing that. Then enable them selectively and have some configuration way to say which kind of events I would like to filter out, which kind of traces I would like to get as part of as part of the loaded traces. It's extensible in the way that you can add new traces as part of pull requests, and that's generally very easy to do. Multiple traces can be loaded, and the good thing is that you don't need to load programs out of file system. Those are all bundled into the binary itself. So, and also supports compile once, run everywhere helpers to unwing namespaces, etc. And the limitations is that it requires running Fluent Bit as root. What is the proposal? The proposal is simple as having a way to define which traces you would like to load. I think as part of the future work, we would like to expand this configuration, as I mentioned, to be able to run and filter particular events that are part of the traces. The API is actually quite simple. So you determine what is going to be your eBPF program and what is the way to handle the events for those programs. So I'm gonna show briefly. Correct. So this is the part of the code that takes part of registering a trace. So you essentially say, what is your trace and what is the handler for that event? That's all you need to do in order to register a new trace. And how is a handle? So for example, for an exec handler, I will have two things as part of the context. One of that is an encoder, a log encoder, and another one is going to be the instance of the Fluent Bit plugin reference itself. So essentially in your handler, you have to check for two things. First of all, that the event type that you are receiving is the one that you are expecting, and that you can have an encoder for that particular data. So the context for event handling, as I said, is you will have a log encoder and you will have an instance of the input instance. So an encoder, I think we can leverage a simplified API for the encoding part, but generally is about setting up the structured members of the event into an encoder body, essentially, and commit that record into Fluent Bit. Okay, so let me do a demo as well about this. Okay, so as you can see in this configuration, I have these three traces: signal or tracing signals, execution, and malloc. I wrote this malloc trace this morning. I would like to go quickly around this. So here's my traces. I have this malloc implementation. Here's the program. And what I would like to touch base here is that in this case, I'm using uprof here for tracing all the calls to this libc. So callocs, realocs, free, mallocs. And then I have some program that will do two things, right? So it will set up memory pointers here. It will await for that memory pointer to be released, and then it will keep track of that. Whenever that completes as a cycle of allocation, it will send that data, submitting that buffer data into a ring buffer. And then I will put different traces across different functions in my system. So I will have malloc, I will have free, I will have realloc, all those being tracked. And the only part that I need as a developer, aside from setting up my eBPF program, is to set up a handler, right? In this case, I call it trace malloc handler. It will set up an encoder. It will make sure there is a type memory. It will encode the event, and it will append it into Fluent Bit. So the encoding will take care of, okay, I want to keep track of the process ID, what is the command, what is the operation that I'm tracking, what is the base address, what is the size of that allocation, and then commit that record. Okay, and then registering that new trace is as simple as using this macro and setting up that handler there. So yeah, and then running this should be as simple as. Okay, so I'm running here in this container. So I will start receiving this information. So it's an operation of type 2. We can have a helper here to translate this type 2 operation into whatever is that. So we can take a look, what is that? Let me see here. So we have includes events. Okay, so we can have like a string conversion. In this case, it's a malloc or a calloc. You will see the base address and what is the size of that allocation. Conversely, you can also enable multiple traces. Okay, so here you will start seeing other sort of events and traces being generated. So signals and other operations. Okay, I think this gives a good idea on what can be achieved, how can be extended, and how's the initial proposal for the API. So yeah, limitations. Obviously, this is something that we are progressing. The amount of traces that we have is ridiculous low. So we have 3 or 4. Might be important to start expanding into other different traces. Also, we make sure that is it compatible with existing programs that we can use, for example, in inspector gadget traces, that we can use Tracy traces as well, etc. And how the community can benefit out of extending that. Map types are limited. We would like to expand to others to do more efficient handling of data instead of using like only ring buffers, probably use some more advanced techniques, using tail calls or chaining of programs. There is no performance counters information, events being collected at the moment. There is no XDP or socket programs. It can handle, also we would like to handle independent collectors rather than one single collector, expand to more traces, and at some point in the future, enable this functionality in the default builds and document it.